Okay, we're going to look at a two-body problem, the classical two-body problem, that has two masses separated by this distance with a potential function between them, u of r1 and r2. And we don't know what that coupling is yet, but we're going to use a couple laws of physics and some symmetry laws in order to figure them out. So the first thing that we're going to do is let's talk about its potential. It could be reliant on either one of these positions for all we know, but we know a couple things about the system. One, it is translationally invariant. If I move this system over to here and write it over here, where this is R1, R2, and M1, M2, with R between them, we know that nothing can change. So this is going to tell us that U is relative, meaning that it is of this vector I have called R, which is the difference between this vector and this vector. Our next thing is that this system is rotationally invariant. If I grab my system and I flip it any way around I want, assuming there's no other external forces or potentials, that means that we know this has to be a magnitude problem because R would be changing if I did that. So we know that the magnitude of R is never unchanged when we flip something around. So we know that U equals U of R. So we're going to keep that in mind. Now, knowing that, let's look at the Lagrangian of this system. Lagrangian is just 1/2 mr1 dot plus 1/2 mr2 dot squared minus U of R. But I don't want a two-body problem. I want to turn a two-body problem into a one-body problem. So let's think about the center of mass. We know that R, center of mass, as a vector, is just m1r1 plus m2r2 all over m1 plus m2, which I will denote from now on as m1r1 plus m2r2 over capital M. So let's replace these r's with values from our center of mass and values of our distance vector. Let's do that. So first we need to solve this equation for r1. So we have mr minus m2r2 equals m1r1. Now let's plug in from here that we know that r2 is r1 minus r. So that will tell us that mr minus m2 r1 minus r equals m1r. Or, more namely, I'm going to bring this up over to here. Let's get rid of our picture. We don't need that anymore. We'll get back to it. More namely, we know that mr minus m2r1 plus m2r equals m1r. Or, factoring this out even a little bit more, we can see that this is mr plus m2r equals m1 plus m2, which is mr. We'll divide through. This is all r1. So let's divide through now. And we get that this is just r plus m2 over mr. This is what r1 is equal to. The exact same argument can be made for finding what r2 is. I'll leave that as an exercise to show that it's r over mr. So let's return to our Lagrangian. That looked like, and then it was r1 dot squared, so that's r dot squared plus m2 over m r dot squared plus 1/2 m2 times r dot minus, no squared here. This whole thing is squared. Let's not be silly. R dot minus m1 over m r dot. This is r dot vector. Let's keep that in mind. All of these are vector equations right now. We'll deal with that later. Let's keep going. So, we can take note now. We can factor these. It gives us m1 1/2. Oh, sorry. Excuse me. Gives us 1/2 m1 r dot squared plus m2 over m r dot squared plus 2 m2 over m r r with a dot between them. These respective have dots. plus 1/2 m2. Exact same thing, replace the m2s with m1s and a minus sign. So we get r dot squared plus m1 over m r dot squared minus 2m1 over m r, where, there's a dot product between these. Let's factor this out and simplify it. So now, I see we have an m1 and an m2 term here. We get a 1/2 m r squared plus, we're going to have an m1 m2 over m r. So this is 1/2 m1 m2 over m r. The m2s are both squared. And from here now, we're going to get plus 2 m1 m2r over m r. If you can note over here, this will end up canceling with this. I leave that as an exercise if you'd like to prove it to yourself by doing the algebra. And here, now, this right here becomes plus 1/2 m2 m1 squared over m squared r. We can factor this a little bit and say that this is 1/2 m r dot squared plus 1/2 m1 m2 over m r squared. These have squareds on them. And then, once again, I'm going to leave it as an exercise. I'll show it here. This is plus m1 plus m2 over m, which we know, this is multiplied by that. This is 1. So, our Lagrangian now, from our center of mass frame, can be written as follows. I use mu here for the reduced mass formula, where mu equals m1, m2 over capital M, which I defined earlier. Okay, now we've gotten somewhere. Minus our potential of r. Notice, this is still a vector r. So, let's think about this now. Let's go back and remember our original system. Right? We know that there's going to be a central force. If we do nothing to them, they will just collapse. So we want to say, well, we don't want this to collapse. So we're going to allow them to freely rotate around each other so that this polar vector r can change with respect to some angle. We'll call it phi for our Lagrangian. And I'm going to make one more step here where we step into the center of mass frame. So all that simply does is make r dot 0. So we can ignore that term in our Lagrangian. That's very nice. This Lagrangian now is something very simple, which is very easy to deal with. So let's take note, remember, that r dot squared is r squared phi dot squared plus r dot squared, where this is the magnitude, this is a vector. So we're going to write that into our Lagrangian. Now let's apply the Euler-Lagrange equations here. I'm going to do one with phi dot first. So what we see is that d dt partial L partial phi dot is just going to be equal to, bring the 2 down, should be left with the time derivative of mu r squared phi dot. This is going to be equal to 0 since there's no phi terms. What this tells us is that the angular momentum of this system is conserved. This is a quantity of angular momentum. So what we can assume from this then, let's start making some notes up here, is that mu r squared phi dot is some constant, we'll call it L for the angular momentum. Now, let's look at the other derivatives here. This says that mu r double dot, that's going to come from this term right here, has to be equal to mu r phi dot squared minus the partial derivative of u of r with respect to r. Okay, we're almost there, home stretch of deriving what the central force problem is for two bodies. Let's apply this, because we know this has to be constant, and plug it into here. So we just get that phi dot is L over mu r squared. So let's apply that to here. This is going to give us a new equation that looks like mu r double dot equals mu r L squared over mu squared r to the fourth minus the partial derivative of our potential with respect to r. Okay. One last step of clarification. This says mu r double dot equals L squared over mu r cubed minus partial u of r with respect to r. This is the differential equation that will solve for all of our modes or our elliptic orbits or anything we want with given a potential. So now we have to go back through and define a potential, and that can be seen in a later exercise. Thank you.